start by looking at the hydraulic system. Really, what I want is to provide you a general outline of various different actuators that you will be having. I think you get to hear a lot about motors. We can use motors to actuate things on FYP. How about did you find that the motor couldn't meet that load, that heavy load? There are other options available, namely hydraulics, or you could even use pneumatics. Why is it that you get to find a lot of that in your FYP room? But you get to see a lot of your friends or even yourself using motors, stepper motors, DC motors, even motors that requires 3-phase. That's because a lot of your FYP are small in nature. You really need to move very heavy objects. I think it's good to know what other options are available, so that when you go out to the industry, you wouldn't only use electric motors. So I'll make a comparison between these various actuator systems today. And we'll start off by looking at the hydraulic system. Hydraulic and the pneumatics, they have a lot of similarities. One is using liquid, it's called hydraulics. The other one, pneumatics, is using air, compressed air. So that's why in your set of notes, you don't get to see one more lecture talking about pneumatics, because a lot of what is happening in hydraulics is interchangeable or can be used for pneumatics. So for the hydraulic system that we're looking at, I think the first thing that comes to your mind for hydraulic system is that excavator and construction site. You're going to see this huge excavator. It has a lot of power. And that sort of action to actuate is actually done by using a linear cylinder. A cylinder is those piston kind of object. It looks very silvery in color when it extends out. The linear form of actuation is just one form. You have a rotary cycle that you get to see. And particularly, we want to have some understanding of the hydraulic system components. There are actually a lot of components that comes in. Looking at an overview of that schematic and how do we go about changing extension or retraction through a single valve. The single valve do the switching between extension and retraction. You have the spool valve operation that's residing inside the single valve. So we have with that, followed by spool valve control, how we go about doing the control, and a little bit of pneumatic actuators. So we think about the link and the links and the joints as the skeleton of the robot. Then your motors, actuators can be thought of as units. So a lot of times you get to see actuators residing in the robot itself. Some advantages and disadvantages. Motor is going to be huge, and it's going to be part of the arm of this manufacturer. So there are some ways that we can do that, namely using there are a few reasons why we use actually
这我可以啊。
What we
保
want to
减
achieve
加
is that we must
加
provide
防
enough
止
power
其
to
他的。
accelerate and decelerate things.
新加坡呢？那太好了，我去那边电视
For
比较
any
好
kind of
看。
actuator, we want it
反
to
正
be
这
light,
个是比较好
economical,
的时候，就是这个
accurate,
时候呢，
responsive,
在什么
reliable,
还可以想
and easily maintained.
Holiday Plaza。
Out of the three types of actuators that we hear normally today,
终于
like
找到
something
了。
like this, you get to do this comparison. So I want you to see, in terms of all these various attributes, how do they match up with each other?
记得会不会只剩下可能是评论。
There are these two types of actuators that we use today is only hydraulics and a little bit of pneumatics, and then we'll move on subsequent lectures to DC motors, DC motors, and stacker.
小聊。
Things that you're hearing so much, really I want you to know how does it operate. The hydraulics actuator usually uses the liquid, and particularly it's oil. There's good reason why it started with that oil. That's because oil itself is a lubricant. So as it extends out, it also lubricates that piston. There's also another reason why oil is chosen. So if you think about it, if it's not oil, then what other kind of liquid is controlled?
Grease.
Liquid.
Grease.
Water can be one of those. And actually, I was using water for hydraulics.
Water 不好，
There's a difference between using water and oil. Water being less viscous is prone to leaking. So there's a small little gap between the seal and the piston. Then the water is going to leak out. The good thing about water is that it's not fire hazardous. In fact, it's not put on fire. So you can use water hydraulics in things like aerospace industry. We have the aircraft crash dump. So it carries within this mechanism is oil products. And the oil is going to add on to the fire burns. So you have even heat. So that water system would help to extinguish a little bit of that impact that would do any fire. Water is actually heat or so there are those disadvantages. So it's a mix of what you want to achieve. So these are the list of advantages and disadvantages. Those that has got a plus sign, those that has got a plus sign over here, they are the advantages. The ones that's labeled with negative, those are disadvantages. If you think about this ratio that's called power to weight ratio, how much power I can get out of the weight of my system, this actuator system. Hydraulics will give you the highest power to weight ratio. What that means is that the amount of power that you can get compared to the weight of the hydraulic system, this power delivered gives you more to that weight There's more than pneumatics, there's more than the actual motors. And that's why we get to see that used a lot in heavy industries, where you need to lift a lot of load. Lifting is just one way to, just one mean of overcoming load. There are other means of overcoming load, like drilling, scratching, turning. All these are some way of trying to overcome the load. So hydraulics is good in that. The robot or the machine itself using a hydraulic system usually wouldn't be a small form factor. A lot of your FIP prototypes that you build are small. We're talking about a truck size kind of system, and for truck size system to overcome whatever loads that you require hydraulic. So heavy payload, large system, the highest power ratio. And last week we were talking about the reduction gear. Hydraulics does not require a reduction gear. Just so because there's not so much power that it can deliver. The other big thing about hydraulics is that if you were to lift something using hydraulic, and once you lift it up, you can actually stop where it is. You do not need to lock it, you do not need to break itself. Later on, you're going to see the circuit itself, it can maintain at that position. You can say that you can be left in position after that lifting without causing any sort of damage, wear or tear or over time, just putting it in that position. So, how about the disadvantages? This is what it is, not for small system because it has a lot of components, reservoir, hose. You're going to see this thing most of the time, which is interesting because why is there a motor in a hydraulic system? I thought hydraulic is just purely the delivery of that fluid. Why is there a motor? That's because in order to deliver that fluid, that delivery, you still need to have a motor to deliver that fluid. That is called a pump. So the pump itself runs on a motor, it runs on electricity. So it doesn't mean that hydraulic system is purely non-electric system. There's still going to be a motor in there. So why is it that the motor could then deliver the kind of overcome the load? Why not use motor directly at the load instead of use a motor to drive the hydraulic? Leave that load. That's because there is this hydraulic advantage that we can derive. There is this thing about, I'm not sure have you seen in your earlier education, when they talk about hydraulic, they have one side, kind of have two tubes connected, and one side has got a plunger, and the other side has not plunger. And this plunger will have a smaller diameter, that plunger will have a larger diameter. So you can use a smaller plunger, press it down, and then you will transfer that fluid over, and you can lift up something that's maybe so there is what we call the hydraulic advantage. So you can gain this kind of hydraulic advantage by delivering liquid or just generally fluid. It's pneumatic to have that advantage as well. So that's why we still would have this motor that can deliver that fluid so that we can get some hydraulic advantage. The hydraulic system, while you can see in the construction site, it has a very dirty environment. That excavator is operating in a very dirty environment. That's why it's susceptible to dirt. The system, the hydraulic circuit, requires a filter to filter out all this dirt. Itself, when the piston extends, there's going to be a seal. This seal is actually to remove the dirt layer on the piston so that it can move it down without contaminating hydraulic fluid. Offers high torque, high pressure, large inertia. Why is it that it's a disadvantage? That's because for high pressure system, if that were to be let's say something hit on that, you're going to have that fluid bursting out. It's under a tremendous amount of pressure. So in that sense, it's a disadvantage if you compare that to the system, there's going to be a large inertia on the actuator, and later on you get to see some mathematics to help you appreciate that. Now let's compare that against the pneumatics. COS stands for commercially off the shelf. So in the industry, you get to hear this word called COS. That means off the shelf items, commercially off the shelf. You don't have to do it. So pneumatics, there are a few major players in Singapore. Maybe some of your peers doing FYP would have approached them already. ASCO is one of them, SNC, so they provide a lot of this hydraulic pneumatic system. Overall, you have this fluid module, fluid dynamics, SMD. So pneumatics, they are usually commercially off the shelf. They are pretty reliable because it uses air, and air is compressed, and it wouldn't cause much damage to the component wear and tear. That's not an issue. Because it's using air, so even if there's a leak or if there's a spark, it wouldn't ignite the hydraulic boiler. So in that sense, it's an advantage. It's good for on-off systems. So if you think about systems that you need to turn on and off, meaning, let's say you want to push a button, use a hydraulic system to push a button, which you can use other actuators to use a hydraulic system to push a button. But just having that as an example, you need to do this kind of thing rapidly. The hydraulic would not be able to respond to that frequency that well compared to your pneumatic system. Your pneumatic system uses compressed air, so it's actually good for this on-off kind of system. For the disadvantages, you have the pneumatic, just like the hydraulic, it requires quite a lot of components to come with it. Things like pressurized air, filter. Later on, you get to see a list of those components. Actually, 2 pages of them in your slides. So that many components compared to a very simple motor. So you got to decide in the industry what is it that is suitable for your case. Would it be motor? Would it be a hydraulic system? Would it be a pneumatic system? And you got to make these comparisons of advantages and disadvantages. The electric motor, it only requires that motor and electricity supply. That's it. So it's clean, it's easy to implement, but it wouldn't give you a lot of power, not even a large motor if you require to have it overcome a lot of load. So you'll be able to decide that after we go through some of the slides. So even though pneumatics uses compressed air, it actually deforms under load because you can actually forever compress that air. It's just that amount of pressure that you use for some. So that amount of pressure comes about from the amount of load that you have. So the larger load that you have, the larger pressure it has to overcome. So that means if I use a pneumatic system, hook it to a load, and if I add in more load, you can see that the pneumatic system starts to deform. That means the air in there will actually get either more compressed or will get more compressed. Out of the various actuators, hydraulic, pneumatic, and your electric motor, the pneumatic will give you the least ratio. That means the amount of power that you want to have compared to the weight of the entire actuator, pneumatic will give you the least. So you don't get a lot of power for that amount of mass weight that's required to build the entire pneumatic system. So it sounds like so heavy doesn't give me that much power. Why would I need it? That's because of some of these advantages. You want it to have a rapid on-off system, or you are in an environment that may have some sparks, then you would want to use a pneumatic system. And also to deliver some sort of actuation. Now let's compare all this with the electric motor. It can be a motor or it can be a generator. So a lot of you would have already started to use electric motor. I'm not sure if you size it correctly, you choose it correctly. There are a lot of different types of motors out there. Are you using the right side motor? That actually will be covered in the later lectures. It's good for all sizes of the robot. Unlike your hydraulic and pneumatic, your electric motor offers you the best precision. You sort of could imagine that because pneumatics is sort of for a very large system. Sorry, hydraulics for a very large system, pneumatics kind of like medium size, and electric motor. If you have a large motor, you can go larger size. Electric motors usually is for smaller size, and you can go down to very, very tiny size. Actuation is required because you can have good control of it and you can achieve the position that you want. You've seen already when we talk about the reduction gears, we can reduce the inertia on the load side. So those are the advantages. And also, it doesn't require much maintenance, as you know, for electric motors. However, that reduction gear itself would also contribute to be a disadvantage because now you have to do the sizing for reduction gears. You have to find out what is the right gear ratio. You must get gears to come in. 2 years ago, I bought a washing machine because I moved to it. So at that time, I was looking at this washing machine and he wrote something over there that got me very excited. It says that this washing machine is not using the gear reduction type, but it's using pulse width modulation. So what does that mean? You know, for a motor, when you actuate it, it's going to roll, it's going to turn rapidly at a very high RPM. And there's actually no way to decrease that RPM by reducing the voltage. You can't do that up to a certain level. And if you continue to reduce that voltage, it just wouldn't actuate it at all. So if you reduce the voltage up to a certain level, yes, the speed will reduce. But then equivalently, the torque will reduce as well, because there's just not enough power required. You wanted to reduce the speed. Why do I want to reduce the speed? That's because I can't run things at that kind of high RPM. So that's why I need the gear reduction for the motor. Reduce it to the speed that is controllable, that can be useful to me. So without using the gear reduction method, there's also another way that's to use pulse width modulation. So we also talk a little bit about that when we come to electric motor. Some advantage that you can get out of using pulse width modulation. And the whole idea is that we can avoid using the reduction gear. The motor in operation would not be able to brake when it comes to a standstill. In fact, if you go to the lab, there are some motors that are asked to or resources to buy. You turn that shaft, it can turn when it's compromised power. That means after it turns to that certain position, you cannot hold it in place unless you have a brake. So this is considered a disadvantage because a lot of times when you want to actuate something, you also need to come to a stop and stand still, let it stay there before the next actuation. Imagine if the load continues to apply on it and you couldn't come to a standstill, then it's actually hard to do your. So those are the introduction for the various systems. The hydraulic system, as I was saying, it requires a pump, so an electric motor is still necessary. This is actually a repeat here. The hydraulic system offers you a high power to weight ratio. You're going to see two types. One is linear, one is rotary. It's good in hazardous environment. You can hold a weight without a brake, or hold a load without a brake, and you can apply torque without a need of a gearing system. So there are more of a leakage issues associated with the hydraulic system. In fact, I visited the Neon Ollie's hydraulic lab. And once you step in, you get to smell this hydraulic oil. That's because they need to do the maintenance work. And on the floor, you get the oil drips stains. So it's actually a very dirty environment when you start using hydraulic. You definitely get phase leakages because of the high pressure. If you're to talk to your chief engineer when you start working, we want to suggest a hydraulic system be calculated because it's costly. It's very expensive. Just so because you need to set up a compressor, you need to have a hydraulic circuit. And the hydraulic circuit hose is actually not rubber hose. Rubber hose is cheap. It's actually metallic hose. So because you need to withstand that amount of brake pressure. So that metallic hose requires that sort of setup, and the hose system is actually a long hose. The valves as well. Valves are not like a manual lever that you can turn on off. It's electronically actuated. So the valves inside the valve, later on we have to closer look. It's a very intricate device. Now, this part here is interesting. I want you to read this sentence over here. Let me read this sentence. And why? Why do you think so? Why do you think that electric actuators, maybe some of you have been using already, you actually size it to your maximum load? Why is it that hydraulic pump, you're going to size it to the average load? Why isn't it sized to the maximum load? That one is interesting because you kind of could probably know how much is that load and then design your hydraulic system to be near to that as well. The key part is actually over here. There's this thing that's called an accumulator. Later on, I'll talk a little bit more about this. In short, accumulator is a device that can store a constant amount of energy, and this energy is in terms of pressure. So whenever in the hydraulic line, if there's a drop in that pressure, meaning no load, then it can do the compensation. And when there is an increase in the pressure line, in that hydraulic line, meaning if there's load, then you can also do that compensation. So later on, you get to see how this accumulator actually looks like. It's just to store that excessive amount of energy in that power system. So if you find that your body you need to have certain kind of motion and you start to implement motors to move certain things, you find that you can't really have a very heavy motor to lift something heavy because it all adds up. Your system will then become heavy. So if you want to carry something that's very heavy, then you'll be looking, oh, my motor, I need to have a larger size. I need to have a larger voltage. A larger voltage means that the motor size is larger. Some of your motors maybe will run on 6 volts, 12 volts. Bigger ones, 24 volts. It's using the charging battery. So all these, your desk DC supply can power it up. But then to have such a big motor, the whole system becomes very clunky. Then you may want to start to consider these motor your best compared to pneumatics and hydraulics. So your motors needs to be near to the joint where you want to move. That's the disadvantage. You can't have the motor somewhere else to move that joint. But hydraulics, yes, you can do that. Your pump can be so far away. What is required over here is just that your valve that can turn it on, off, to switch extension or retraction. So your arm over here relatively will become a lot more lighter. So for hydraulic system, your power unit can be illustrated, hence reducing the mass and the motor inertia. I have this video clip. Hydraulic actuator is not just a linear type. There are also rotary type. So I'll play this clip and you can have a look. ，there's no sound for this. So there is a housing over here, shaft. This one is a vein that's connected to the shaft. This shoe over here is not moving. There's a seal. And there are going to be 2 ports over here. So this port here is going to be energized so that this vein here will start to rotate. So we are looking for rotary hydraulic system. So over at the port here is liquid, usually hydraulic oil, that will come in. It will be pressurized in there to move this or to rotate this shaft through applying the force on this beam. And this side here doesn't mean there's nothing. There's also hydraulic oil over here. It's just that when it's energized over here, this hydraulic oil here will get pushed out to the atmospheric direction. So this part here is the one that's under the compressor pressure. So let's have a look. Pressure in, it pushes it out, it rotates. After that distance, and you can reverse that pressure using the valve, and you push it out. And you can repeat this kind of cycle to rotate clockwise, rotate anti-clockwise. So some of you may be thinking that this is useful, yes, rotary, yes, but not quite useful because it cannot rotate continuously. Right? You can only do that like 280 degree rotation and then come back 280 degrees. You cannot do this continuous rotation. I want that continuous rotation that the motor would offer, because it's hydraulic, it's going to give me a lot more power. Yes, there are other mechanisms that can do that, but in your lecture material, it's actually not covered. So we only look at this case where this pushing is being. There's another type that I was using, has a lot of pistons in between, and then you can rotate continuously using hydraulic fluid. Those are called hydraulic pistons. Hydraulic. Yeah, your peers really want to listen, so you gotta give them a chance. Okay, let's look at this mathematics, right? Because the notes only give you this final form, there's no picture, no nothing, so I thought it would be easier for you if I do a sketch. So I'll be using that diagram over here, right, to give you a sketch. Let's have a look. So you have that beam, that shaft. So the shaft would have certain length. I'm just going to draw a section of that. And you have this beam over here. That way. So I'm going to take this direction as R, and this beam is going to rotate within that cylinder. So we call this R2, this one over here is R1. This inner shaft radius is R1. And it's going to rotate with a certain amount of torque. And what I'm going to do is to look closely at this surface over here. That surface. Because this surface is where the pressurized input is going to impact on it. And because it's over that surface and is rotating, so we can expect that the pressure, amount of force that this vein experiences is going to vary across that radius. So over here, the force, and over there, the force is going to be different. So what I can do is to take a small little element over here, this elemental surface. So I'll sketch that elemental surface over here. And this elemental surface will experience the force that's acting on it. So I'll give the dimension of this. This will be the length of the T, and that small little radius over here, I call it dr. Just an elemental little radius. So over here, this part here, that is T. Sort of like the thickness of T. So the force will be equal to pressure multiplied by the elemental area. Because pressure is equal to force over area. So force is equal to pressure multiplied by area. And that area is elemental area. So if I look at this elemental area shaded in black, that will be T dr. That's my area. So if I want to find out what's the torque, torque would be force multiplied by the radius. That will give you the amount of torque. So in my case, I will have force here, that's going to be P, T, dr. And then I have my radius that I put in here. And what I'm going to do is to integrate this from R1 to R2, so that I covers this entire shaded surface over here, from R1 to R2. So let me solve that. PT is a constant, so I'll bring it up. R, integrate R, I get R squared over 2. and that's for the limits from R1 to R2. So if you substitute that in, you get PT, take that 2 out, and you get R2 squared minus R1 squared. So that's the one that's provided in your lecture notes. Yeah, PT over 2 bracket R2 squared minus R1 squared. Okay, these questions that I have for you. If you think about it, this thing is being pushed. And there's a certain amount of volume of fluid that needs to come in order to push it. And this amount of volume will control the amount of displacement. So the larger volume that is inside is pushed in, the larger volume it is, the more this vein will get pushed. That means the more displacement you get. So volume can be related to the position of your shaft. The other part, how about flow rate? What do you think flow rate controls your shaft? So just now I was saying volume, the amount of volume of the fluid that's going in to push the vein, the volume controls the position of the shaft. How about this flow rate? Faster flow rate, slower flow rate. What do you think controls the shaft? You gotta control the rotational speed. So we can make use of these two factors in order to control how our shaft would respond, both for position and both for speed. So let's have a closer look at the mathematics behind this. So I'm going to do a sketch as well, because this part is also giving you just the formula, so it's hard to imagine. So I have this outer cylinder, and I'm just going to look at one of this inlet port. So this inlet port will have a diameter just like D, and this is the center where the shaft is, and this is where the plate or the vein is going to be, and I have an output over here. So there's inlet and then it can be outlet or inlet. So let's take this as one inlet, and then this one is one outlet. So whenever there's energized fluid coming in, you will press that outlet, you will press this vein, and then you will rotate. Now this is actually not a vein, this is a shoe. This is a shoe, and then the vein is over here. This is a vein. And this one is the shoe. So the shoe will be fixed. So whenever it's energized, then the vein is going to rotate in that way. Rotate that way. So hence pushing out the fluid over here. So I'm going to take the segment of this cylindrical segment that I call is a dx length. So if I look at this and say that what is the volume of that? The volume of that would be pi d squared over 4, which is the surface area, the cross-sectional surface area. And multiply that by dx, that will give me the volume. So this is the one that controls the volume, and and it controls displacement of the rotary vane. So it's a position control strategy by changing the amount of volume. Let's look at the other one, flow rate. Flow rate, volumetric flow rate particularly. For volumetric flow rate, that will be dV dt. The volume change over time, volumetric flow rate. So I could differentiate V with respect to time. So I'm going to end up pi d squared over 4, which is a constant, and dx dt. So I could express this as pi d squared over 4 x and dot. The dot means rate of change. So what I have over here is that this controls the flow rate, and what that means is that it controls the velocity of the rotary vane. So the rotary vane is this one. Rotary vane. So the next couple of pages outlines the components that you can find in a typical hydraulic system. And later on we get to see one of these components, hydraulic component, that's called servo valve, and how it operates. In order for it to energize it or de-energize it with fluid, there's something that needs to come into it. We call that a servo valve. So some of these components that will go into your hydraulic system, I've actually put down this hydraulic schematic. You don't have to memorize that. It's something that I added on. Your class code notes actually don't have that, so I added stuff so that you could appreciate that there's a huge volume of knowledge behind the hydraulics. They have this kind of funny symbols to complete that entire hydraulic circuitry. So let's have a look at some of them. The hydraulic linear actuator is usually represented by this cylinder over here. Typically, there is a cylinder and a piston that way. And you have an inlet of the supply that way. So that's a schematic for your hydraulic cylinder. If you look at a rotary actuator, that's how it's being represented. This double arrow over here shows that it's a rotating device. So they are controlled by your servo valve that we get here later. And we can also use manual valves to do the control. There's going to be pump, motor, and cooling system, and a reservoir in the entire hydraulic circuit. So later on you get to see some of these words again. Why do you think we actually need cooling in the hydraulic system? This is unlike electric motor. The electric motor will not need any form of cooling. But if it's running by DC, you tend to have, or actually high power, you tend to have cooling pins. But you do not need to actively cool it. For the hydraulic system, especially hydraulic, the oil will actually get heated up when it's actuated, because there's tremendous amount of pressure that's used in order to do the weight lifting. So that amount of pressure and actuation would heat up your hydraulic fluid rapidly. And we really would need a cooling system to come in between to cool down that fluid before it goes back to the reservoir. And that's why we need this cooling system coming. Now this is the interesting part I was talking about, and in fact this figure over here is something that I added in. This is how the accumulator works. It's used to store the extra energy for maximum payload, and it also can be considered as a pressure storage. So if you have this thing over here, the dark one, this one is called a bladder. You may have heard about bladder before. In your body, there's actually a urine bladder. It's kind of like an elastic bag. So what we do is that we pressurize this elastic bag, pressurize it up to a point that it closes this valve over here. So this elastic bag will press against this valve and then close the system. So whenever the system experiences excessive pressure, so much pressure that pressure is larger than this bladder pressure, what's going to happen is that it's going to pop this valve and it's going to compress that bladder because the system has pressure that's higher than this pressure inside the bladder. So when that happens, it actually relieves the pressure in the hydraulic line. So that's the job of the accumulator. If there is a drop in that system pressure line, and pressure is demanded because you need to lift heavier load, and what's going to happen is that this bladder here will start to expand out, and then it's able to supply that constant amount of pressure to your hydraulic line, so as to maintain to hold it under this external, to hold it under pressure by the external source. So that's what the accumulator is used for. If you look at PUD, our water supply also has an accumulator. In the past, you get to see this kind of the water pipeline. Suddenly, this huge vertical cylinder is sticking out. I'm not sure have you noticed, but that's the accumulator. So the pressurization of this air is not done continuously. It's just pressurized for one time and then it's sealed up. So it's inside. This huge cylinder is connected to the water pipe. That's to supply constant pressure or to accommodate the pressure fluctuation due to the demand and due to the compressing supply. In order to control all this actuation, later on you get to see this servo valve. Maybe I'll zoom in a little. So this servo valve is interesting. You could see it in two ways. This one is in the non-energized state. So there'll be two lines that's connected. Maybe not there. Two lines like that that's connected to your cylinder. So it may be done in this way. The cylinder is here. So you can see that what you need, it's not very clear. Let's take it out. So you have that cylinder that's supplied that way. So in order to push this cylinder outward this way, I need to energize here, and then this fluid needs to come back. This is sealed. Right. So in order to energize it the other way around, this way, then I need to energize here, and this one needs to come back. So this servo valve allows us to do that job. How does it work? So there will be actuation by the side to move these three boxes, either all of them to the right side or all of them to the right side. So let's have a look at one of them.
Right side to the right side.
If it's actuated in this way, Move the entire box to the right side, so you have this coming down that way. So what's going to happen is that this is going to energize this piston to move to the right left. It's energizing it this way. It's going to move the piston to the right or the left. It's going to move to the left. Right? And if it's energized in the other way around, and you can see that it's going to move the piston back to the right. Yeah. So that's what a servo valve is doing. So later on, you get to see that. There are other components as well. Check valves is to control the maximum pressure. Holding valves to prevent the actuator from moving when the system is off. Connecting hose, filtering system, and whatever sensor that is required in order to sense as a feedback. So you have learned about that sensor section already. So we started with sensor, and now we are at actuator. So whatever sensors, they will have different kind of symbols, so I didn't include that symbol. Let's have a look at this pressure, entire hydraulic system, pressure monitor. Now over here, what is not included is this electric motor. So your electric motor will drive your hydraulic power unit. And I kind of sketched two arrows, so it depends on what direction we are looking at. So let's have a look at the source. It's going to supply that energy to this servo valve. And the servo valve would have a motor to move those three boxes that you saw just now. So assuming that this one will flow through in that way, so there's a double arrow over here. So really it depends on which direction. So let's assume that it's going this direction first. So it's going to energize it and it's going to move the piston to this left side. Right? Energize it and then it's going to flow back that way. So if you move the other way around, that is to energize it such that this one is the one that's moving that pressure, and then you will retract your cylinder to the right hand side. It's going to come back, and then it's going to go to the return line. So your source and your return line is always going that way. But after your servo, then it depends on are you actuating it, using which part of the servo valve. The servo valve will be supplied by the movement of those three boxes. It's actually supplied by your servo motor. So you have a controller to provide that signal, and a sensor that you can place over at your piston so as to provide that sense data to your controller. So it's 10 o'clock, let's go for a quick break and then we'll be back to look closely at the servo valves.